Yes, now let's look into the AVR status register. So we have seen some examples of how to program the AVR to get to access the IO ports, like to read some value, also to write some value. How do we configure the DDR register, which is a direction control register, and the port input register is actually pin register, and output is port A, port B, port C, and port D, so on, depending on which port we are accessing it. So let's move on further. So here is the AVR status register, which is called as SREG. So as you can see here, this is the register that I'm talking about. SREG is an 8-bit register. So what this register basically does is it indicates the status of some arithmetic operation. For example, if you're performing an addition, and usually certain parameters we watch after the arithmetic. As you can see here, these instructions are there is a carry flag, there is a zero flag, there is a negative flag, and there is an overflow flag. There is a sign flag and half carry, bit copy, and global interrupt enable. So these are the some of the bits that are actually available for us. So let me take you to the each one of these flag once. So what does it mean? See, let me start with the carry flag. So carry flag, how it affects? Carry flag is usually affected whenever there is a carry over from the 7th bit. For example, if you are adding certain number, so let me take up an example. So a carry flag, if I consider a number, let's say let's say 59, then I'm going to add, let's say, another number, A2. So what will be the answer? So if I'm adding these two number, I get some answer. So if I have to write in the bitwise pattern, I will write it as, so let me write it as here. So 1 0 0 1, that is 9, and 5 is 0 1 0 1 1 0 0 1. This is 59, and 1 0 1 0 is A, and 0 0 1 0 is 2. If I'm adding this number, let's add 1 1 0 1. This is what I'm going to get. So this is actually D0 bit, and this is D3 bit, and this is D4 bit, and it is D7th bit. So if there is a carry over from here, this point, and this is called as the H flag, this is half carry flag. If there is a carry over from here, this is called as carry flag. So if you're getting a carry out here, so here in this case I get here 1 1 1 1, so there is no carry flag is 0. So that's what the meaning of the carry flag. Zero flag indicates the negative, I mean, if the zero, the result of this 8-bit becomes 0, that's actually zero flag. Negative flag indicates the answer. Okay, if you are adding certain value, if the answer comes negative, then this flag will set. Overflow flag, usually for assigned arithmetics. So whenever you add two positive number, and if your result is negative, that is the MSB bit shows it as a negative. And if it is beyond the boundary, for example, I'm adding a number, let's say 7F. I'm adding a number 7F plus 1. I'm adding this. So my result is 80. Actually, I'm adding two positive number. These are two positive number, and I'm getting the result as negative number. So this is indicating it as overflow. So you have your number, you are adding two positive number because MSB bit is 1 here. So that's how you treat positive and negative number. And you are adding two positive number. If your result becomes negative number, that indicates overflow flag. Similarly, the sign flag. So sign flag is indicating when you add two positive number, if you get the answer as positive, obviously the sign flag will 0. If you are adding two numbers, okay, one may be positive, one may be negative, depending on the magnitude. If the result comes in a proper sign, then the sign flag will set. So there is one temporary bit here, and there is a global interrupt bit. So that's it about the interrupt flag, that is, sorry, the AVR status flag. So where the another name of the status flag is SREC. Okay, so that's it here. Then we will move on to the next example. Show the status of the Z flag during the execution of the following programs. So you have here for 4 loaded to 20. I am decrementing it 4 times. So if you are decrementing it 4 times, obviously at the end of this instruction, the R20 becomes 0. So you can just look at this. So 0 flag is becoming 1 because the result is 0 here. That's how the decrement instructions work. Show the status of carry, half carry, and 0 flag. So we need to add it. So it is an example is shown, added here, and main objective is to find carry. So there is no carry out here, so carry flag is 0. Half ago there is a carry bit gone here, so that is 1. So that half carry is 1. Result is non-zero value, so 0 flag is 0. Here is another example, you can just work out. So given certain value here, add it, and you just see here result is 0. So that's why the 0 flag is set to 1. Another example similar to that. Let's move on to some instructions using the flag bits. Okay, there are instructions. So branch if carry equal to 0, branch if carry not equal to 0, that is branch if lower, branch if higher, branch if equal, branch if not equal, branch if negative, branch if it is positive. So these are all some instructions, okay, depending, checking the based on the flag bit. So we can use these instructions obviously with certain arithmetic operations. So before this, we should have some instructions, could be add or subtract, something of that. Then we can have these instructions just after that and make a decision based on the logic. So let me move on to some data types, okay, AVR data types. So always in AVR, the registers are 8-bit, so data type I is 8-bit. There is no doubt. So you cannot have a double word, 16-bit data types declared anywhere, only for a special case. But most of the time, the AVR data type is 8-bit. And representing those 8-bit, you have 4 formats: the hexadecimal format, binary representation, decimal, and ASCII. Look at this, how the way it can be declared. If you are loading certain register, let's say R28 to be loaded with some value, I can put it in hex, just indicating $75, which indicates another way of representing the number, or you just say 0x75. That's also one of the way. So that is hex representation. Binary representation, you just start with 0B and write all the 8 bits here. So that's how you represent in the binary. So it is equal into 25 here. So this is 0010 is 2 and 0101 is 5. Another representation is decimal representation, where you simply represent the number. Remember, if you are loading any register, let's say LDI R16, if I say 25, then it doesn't mean that I'm loading $25. The 25 is different. If I specifically want hex number 25, then I supposed to load. Otherwise, 0x25 is different, is not equal to 25. 0x25 is 0101. This is 25. Whereas this 25 is exactly the binary 25, for which I can write the value is at as for example, okay, so 16. So how do you calculate? So this will be the 8 field, this is 16, so this will be 1, then I should write 1 0 0 1. Okay, so if I am putting it in the 8-bit fashion, so this is going to be my number. Okay, so hexa number for 25, this is the binary 25 that I am writing. What is the hexadecimal number? It is 19. So 19 hex. So what happens here? So R16 will be loaded with 0x19 when I am writing this. So I should carefully see what you are intended to load. Is it decimal 25 you want, or is it hexadecimal 25 you want? So based on that, we can represent this way. Okay. Then finally, you have one more, which is ASCII. So it's pretty easy to write any value in ASCII. Just put it in the quotes. So value will be loaded. For example, if you wanted to load 2, then the ASCII equivalent of 2 is 32. If you want to ASCII, if value you want to send it as A, then you can send the ASCII value as, so if you are sending the ASCII value as A, then it should be 41. 41 is actually the ASCII value of A. Similarly, small letter A is 61. So that ASCII table will change. So if you don't have to worry about what is that number, you just simply put it in the single quotes, the automatically value will go. Then there are certain assembly directives that also we use, like to define certain constant parameters. We use .eq as count. So wherever the instruction comes with that value, then it will be, for example, if I'm say LDI 21 count, then the count will be replaced with 0x20. That's how it works. So any value we can define, like we use in C hash define. So it's actually .eq. There's one more called .origin. So if you are declaring that, okay, you want a certain code supposed to start with certain location, then we usually start defining that location. And remember one thing, the assembly directives are not the instruction set. They are not the instruction set. The processor will not come to know what an assembly directive is. It is actually the assembler that decides the meaning of it. So before compiling the code for assembly, the assembler will decode all these things and puts the appropriate values there, and then give it to the controller for processing it. So similarly, origin. So if you wanted to assemble the program from a particular location, just write it as .org, say 100, then start writing the instruction. So you are originating your location from 100 location onwards. Similarly, if you want to define certain registers, like if you maybe some parameters like say pin B dot 0, if you wanted to read only, so this may not be defined, so then you have to define it as .eq. You need to define .eq, say pin B dot 0 equal to, then you should write the address of this. Okay, so that will be replaced in the instruction. So these things will be done in a file. Okay, most of these things will be done in the file. So define it is something like we use a header file for a C program. So I can use those variables wherever I need as it is by the name. So this is about the some of the programming aspects, including the status register, some of the branch instructions, and some of the assembly directives, and the way of representing the data types. Okay, so that's it for now.